Hello everyone, my name is Seemaji Arella. I am a PhD candidate in the Department of Computer Science and Engineering at University of North Texas, Denton, USA. Today I will be presenting my research paper, Fortified-Edge 5.0, Federated Learning for Secure and Reliable Puffin Authentication Systems. The outline of my talk includes introduction, collaborative edge computing, the security challenges and the motivation for this research, the concept of fortified edge, federated learning framework, experimental setup, results and analysis, and conclusion with a discussion on the future research. Before going to the introduction, I'd like to discuss something about smart cities versus smart villages. So smart cities is considered as an environment which has more dense cyber-physical systems. The design cost and operation costs are high and the energy requirement is high to support all these applications. While a smart village infrastructure is not as good as a smart city, it has very less cyber-physical systems, the design and operation costs are low and the energy requirement is low. A smart village like smart city supports a lot of applications like smart agriculture, smart irrigation, smart healthcare, smart homes, smart education, etc. But it doesn't have the infrastructure similar to a smart city. That gives rise to certain challenges which are environmental, technical, demographic, political and economic. But the technical challenges that comes up due to the lack of infrastructure are high energy requirement, security and privacy, latency and bandwidth. What is collaborative edge computing? To address all the challenges of a smart village, the concept of collaborative edge computing evolved, which enables the smart village applications to work in a resource-constrained environment. So what is collaborative edge computing? Collaborative edge computing is where the edge servers or the edge data centers collaborate with each other to get a process or a task done when one of the servers is overloaded with more number of tasks. So the collaborative edge computing has the advantages of a distributed environment and smart control of heterogeneous network. It can reduce the bandwidth and transmission costs and provide seamless processing through load balancing. So the load balancing is where one of the overloaded processor or a data center can offload some of its tasks to the neighboring or the next available data center or a server which has less number of tasks or which is at the idle state. So since collaborative edge computing can solve these problems of task processing, it comes up with its own challenges. So the main challenge we are looking at is the resource constraintness and security and privacy. So load balancing and task offloading and scheduling can solve the resource constraintness of this smart village or a collaborative environment. It also gives rise to the problem of secure authentication and authorization, because at the real time one of the processor or edge server which is overloaded with the tasks has to immediately transfer the tasks to another available data center or a server at a different location. So it has to do it dynamically and on real time. It needs to immediately authenticate the neighboring data center in order to transfer the tasks. So we are aiming at developing a secure authorization and authentication protocol which is based on certain security principles. So we are trying to implement security by design, which means the security should be a part of the system or the device from the initial stages and not as an addition in the later part. So security should be an integral part of a device. And the security protocol should be lightweight, low power consuming, which is suitable for resource constrained environments. And security should be provided throughout the life cycle of the device. And we can use latest available technologies to provide extra protection through threat detection and monitoring of the security system. What is secure authentication of edge data center in a collaborative edge computing environment? From this figure, we can see that at the edge layer or the device layer, we assume we have PUF-enabled IoT devices. And the edge infrastructure, where the edge processing takes place, we have different data centers are also enabled with PUF modules for secure authentication and authorization. During load balancing, one of the edge data centers, which are numbered from 1 to 5, have to collaborate with the other available edge data center in order to forward the tasks. So before forwarding the task, it has to establish that the neighboring edge data center is genuine and it is authorized, and then there should be a secure communication established in order to forward the tasks. So we are developing a secure authentication and authorization protocol using the PUFs, which are physical unclonable functions. Our long-term vision is to develop cybersecurity for smart villages based on the security by design principles for secure resource sharing in the collaborative edge computing environment and use of artificial intelligence and machine learning for cybersecurity in smart villages. What is the key idea of the fortified edge? The fortified edge is aimed at developing lightweight secure authentication scheme for edge data centers during load balancing in a collaborative edge computing environment for smart villages by using technologies like security by design, machine learning, and hardware assisted security. I'll walk you through the development, research and development so far in the fortified edge concept. So the first paper was Fortified-Edge 1.0, where we implemented a PUF-based certificate authority for secure authentication and authorization for edge data centers in real time or in dynamic load balancing scenarios. In Fortified-Edge 2.0, we added the feature of machine learning for continuous edge data center monitoring and intrusion detection. In Fortified-Edge 3.0, we tested the system with multiple machine learning models to evaluate the best model suited for processing at the edge. In Fortified-Edge 4.0, we addressed the reliability issues in physical unclonable functions or PUFs. So PUFs are very sensitive to environmental factors like rising temperatures, hot weather or freezing weather, storms, seismic activity, and so on. So these external factors cause some of the bits in the PUF response to flip. Even though if the PUF module is genuine and not tampered with, the external factors may sometimes cause the PUF responses to flip. Once the PUF response is flipped and it is not the same anymore for evaluation, like authentication or authorization. So even if the module is genuine, it will not be authorized. So we have to address these issues by implementing a model which can detect this bit flips and correct them. So we have used the machine learning model to detect and correct the flip bits in the PUF response. The advantage of using a machine learning model is, though there are conventional error detecting and correcting systems like error correction codes and fuzzy extractors, they add to the area overhead and computational overhead of the device. So this is not suitable for a resource constrained environment. We have to come up with something which is lightweight and which can be processed at the edge without any computational and area overhead. So a suitable machine learning model was developed which can detect this of errors and correct them. This is a short summary of the research so far, and in the current research we are exploring federated learning for PUF response bit error detection and correction in a distributed environment. Fortified-Edge 5.0 motivation. So in this image we can see the framework of the federated learning. So federated learning can be of three types. One is cloud-based federated learning, the other is edge-based federated learning, and The third one is Cloud Edge Federated Learning, and we can use this model based on where the model parameters are aggregated. In cloud-based, it is aggregated at the cloud server, and in the edge-based, the local models are trained in the local, and the parameters are aggregated at the edge server node. In the Cloud Edge model, the model parameters are aggregated at the edge as well as the cloud. Advantage of using federated learning is it is a framework suitable for distributed ecosystem, and it gives scope for decentralized training, privacy preservation, and collaborative learning. Here we have done some related prior research on different fields. The applications are different, where they have used different type of data set, including the Adobe stock images, medical image data set, and the KDD Cup 1999, and the current research for Fortified-Edge 5.0, we are using a 100K puff response dataset, and the algorithm we are using is K-mer sequence. K-mer sequence is largely used in genetics and studying DNA sequencing. The novel contributions of current research are exploring federated learning for edge computing in a collaborative environment, federated learning model training, which is efficient in computation and power consumption, proposing a federated learning based framework for puff bit error detection using a machine learning algorithm, and exploring machine learning model and training it using natural language processing approach, a global model aggregation through parameters, and global and local model training and testing on edge devices for computational efficiency. Coming to federated learning at edge for puff based authentication. So here federated learning is of three different types. One is horizontal learning, the other is vertical learning, and the other is federated transfer learning. In horizontal learning, the feature space remains the same, but the data sample space are different. In vertical federated learning, the data sample spaces are same, but the feature spaces are different. And in federated transfer learning, we can have different feature space and different data sample spaces. In our research, we are using horizontal federated learning, where the feature space is going to be the same, but we are working on different data sample spaces. From this image, we can see that in the local puff-enabled devices, we consider that all the IoT devices at the user end are enabled with puff modules. They generate their own set of CRP data. This CRP data set are trained using the local models. These local models update the global model with their features. Once the global model is trained and fit on the received features, it will transfer the model to the available local models, so that each local model will be able to receive the updated model with updated feature spaces and can work on different sample spaces generated from their own datasets. This is the proposed federated learning framework. We have we can see three models in this figure, which is using their own datasets. There's dataset A, B, and C. Each local model is trained with its own local dataset, and the parameters are sent to the global model for aggregation. We are using federated averaging for model aggregation. Once the model is aggregated and fit, the model is transferred and all the local models are updated. Coming to the process flow. As the first step, a local model training is conducted. The local model uses the local CRP dataset, and we are employing K-merge function, which will read the binary puff sequences and then split the sequences and vectorize them. These vectorized sequences are classified using the multinomial NB classifier, and different classes of the features are created. And when the model is completely trained, we can test the model with the input response which has errors, and the model will be able to correctly detect the erroneous response and then correct it. Coming to the federated framework, we are using a Flower AI as a federated learning framework. Using the Flower AI, we have created a client and a server model. On the server side, the server can select the number of clients. The maximum number of clients we have used here is 10. And when the server is started, it will request initial parameters from random client. So if the server receives the model parameters from the clients, it will evaluate it and fit and then send the updated model to the local clients. On the client side, it will work on its own dataset, train the local model and send the model parameters to the server and wait for the updates from the server. Once the client receives the update from the server, it will start fitting and evaluating the model and update itself. For this experimental setup, we have used a 64-bit arbiter puff architecture, and the puff is implemented in a previous research, and we have used the same puff, and Xilinx Basis 3 FPGA is used to build the puff. And for the clients, we are using Raspberry Pi 4, and the number of clients is 10, and we have used the Raspberry Pi 4 as a server as well. And Flower AI framework is used for federated learning model training and testing, and each client is trained on a 10K puff response dataset. Coming to results and analysis, from the image on the left, we can see that a 10K puff response dataset which is fed to each 10 client, and the classification of data. The local model, once it applies a k-mer sequencing and multinomial NB classification, it will classify the 10K data into 100 unique groups or classes. This is the confusion matrix created after the application of the multinomial NB classifier. So the binary sequences are classified based on features. The feature space generated for the local model is 506, and each of the 10 clients are trained on a 10K dataset. Coming to the federated learning model analysis. The local model, like I said, is trained on 10K dataset. 80% of the data is used for training and 20% for testing. The model, after the evaluation, can efficiently predict classes of new responses and be ready for client-side evaluation. To test the overfitting of local model, k-fold cross-validation is done, and the accuracies obtained over 5-fold cross-validations are 98.75, 93.3, 99.3, 99.65, 99.8 and 99.35 with a mean accuracy of 99.37%. Coming to the training times and power consumptions. We have done the separate evaluation of client side and the server side. So three server rounds are repeated in fitting the model parameters from 10 clients with 0 failures. The total time taken by the servers to fit the global model is 154.62 seconds. The server evaluation is increased for 10 rounds and the time taken to complete is 202.32 seconds. On the client-side evaluation, an average of 99.45 accuracy with 0 loss for all 10 clients. And the total time taken for local model training with initial parameter update is 6 seconds. Total time taken for model update over 10 rounds is 130.42 seconds. About the power consumption, we tested the Raspberry Pi 4 with the ideal power of 3.7 watts, and the average power consumed for local model training was 4.5 watts. Here is the comparative analysis with the state-of-the-art literature where they use federated learning model. So the current research Fortified Edge with the K-merge sequence shows an accuracy of 99%. Coming to the conclusion, we have evaluated that federated learning framework is easy, scalable and secure and enables the use of machine learning algorithms for local model training. The use of federated learning for puff bit error correction has shows enhanced performance and prediction accuracy while maintaining data privacy and security, because we are not transferring any puff responses across, but we are only transferring the features of the puff response. And it is highly suitable for a collaborative environment. The CRP dataset need not be stored locally. So like I said, in a collaborative edge environment, where if we are using the challenge response based or the puff based authentication schemes, we need to store the challenge response dataset of each device in locally. The use of federated learning removes the necessity to store the CRP dataset locally, because instead of sharing the challenge response data, we can only communicate the features of the generated responses. And the accuracy and power consumption evaluations also prove that the model is suitable for edge deployment. Future research, the model can be further improved with secure ML model development strategies to preserve security and privacy. The research can be taken forward to explore applications like deepfake detection and data forensics, because the K-merge sequencing machine learning model is very effective in catching the bit variations. And secure communication and authentication with minimum data exposure. All these features can be used to develop smart and sustainable security solutions. Thank you.